In this video, we're going to look at notation for permutations and combinations, because we know that mathematicians do love their shorthand. So we've looked at permutations and we've looked at combinations. Now that you have a sense of what's going on with each of those, we're going to look at some notation for them. The generic form of the notation for permutations is like this. And now we say NPR, but the N is a subscript and the R is a subscript. So those are the ones that are usually numbers. The P always stays a P. So for example, you could have something like 10P3. And so that means you have 10 items and you're choosing 3 of them to permute. This is what you would use if, like I've mentioned in a previous video, if you have 10 cars and you want to figure out how to choose 3 of them and park them into a 3-car garage. That would be a 10P3. Since we've already looked at that example in a previous video, you know how to work it. This is just the notation to indicate that. Similarly, the notation for combinations is in CR. So the same idea is that we use the C to indicate that it's a combination. So for example, you might have 10C3. So that's saying you have 10 things and you want to know how many different ways there are to choose 3 of those things. So like I said, with the 10P3, that is like answering the question, if I have 10 cars, how many ways can I decide to park 3 of them in my 3-car garage? So the way we saw this calculated out was, well, if I have a 3-car garage, I have 3 slots. If I have 10 cars, I have 10 choices for which one goes in that first garage, leaving me with 9 choices for how many goes in the second garage. And then 8 choices for how many goes in the third garage. We just multiply those up. That's going to give me 720. So the notation doesn't change anything about how you calculate it. It's just a shorthand way of writing what it is we're talking about. So the first number represents how many total things we are working with, and then the second number represents how many of those I'm going to permute. Or you could think of the second one representing how many slots you're trying to fill. As we've seen, combinations are not about putting things in order, but just selecting things all for the same outcome. So for example, if you're trying to answer the question, if I have 10 friends, how many ways can I choose 3 of them to go to the movies with me? And this is where we talk about we're still filling 3 slots, but everyone's getting the same outcome. Everyone's going to the movie, so we say order doesn't matter. But I like to talk about it in terms of the slots aren't labeled, aren't named. So here we still have our 3 slots. I have 10 choices for who I pick first, 9 choices who I pick second, and 8 choices for who I pick third. And we multiply that up according to our fundamental counting principle. But with these, the order doesn't matter. So this is where I have to divide off all the ones. I have to divide off all the repeats that are based on just rearranging the same 3 friends. And so the way you do that is to divide by the number of things you're permuting. So in this case, you would divide by 3 factorial, which equals 6. So when you calculate that out, you get 120. Now, oftentimes, both of these notations are also related to a formula that's expressed. So I want to talk a little bit about that, and then I'll let you try some of these problems on your own. Alright, so I've gotten rid of the story pieces, and I'm going to kind of fill in the formula parts of doing permutations and combinations, and I left what we have done already at the bottom so that in the end you see that we get to the same place. So with the permutations, the formula is given as n factorial divided by the quantity n minus r factorial. When I do that with the 10p3, what that looks like is 10 factorial divided by the quantity 10 minus 3 factorial. Well, 10 minus 3 is 7 factorial, so I'm going to simplify this down a little bit. That gives us 10 factorial divided by 7 factorial. But what we saw in a previous video, that basically what that means is that 7 factorial is going to cancel off all of the 10 factorial part that's below 7. Let me write that out so you can see what I mean. So you get all of that when you expand out the factorial, but what I'm saying is 7 divided by 7 is 1, 6 is 1, all those cancel down to a 1, leaving you with 10 times 9 times 8, which is what we had originally when we just looked at filling in the slots. So that's how the formula works, and that's how it relates to how we've already looked at doing these things. I'm going to go through a similar process with the combination. So the formula for the combinations is given as n factorial divided by the quantity n minus 1 factorial times r factorial. So this one has a little bit more to it than combinations, but if you look here at our combinations formula, then that's this piece right here. That's just the combination piece. And then the divided by r factorial is just this divided by 3 factorial piece where you divide off the number of slots, because that's how many different overcountings we get, because the rearrangements of the individual guys makes no difference because all the slots got the same name. Let me go through the work on that so you can see how it gets down to the same thing we already did before. So when I apply the formula to 10c3, I get 10 factorial divided by 10 minus 3 factorial times 3 factorial. Then, like I did over on the permutation slide, I can simplify the 10 factorial down to a 7 factorial. That gives me 10 factorial divided by 7 factorial times 3 factorial. Now, I'm not going to expand out the 10 factorial and the 7 factorial because I've already done that over under the permutations. I'm just going to tell you to imagine such a thing, in which case you're just going to be left with 10 times 9 times 8, and then that just deals with the 10 factorial, 7 factorial piece. That gives you the 10 times 9 times 8, and then you have the 3 factorial piece there. So hopefully you can see how that's all coming together using the formula. I don't regularly emphasize the formula starting out because I want you to see why the formula is what it is, because I'm a firm believer that if you understand why the formula is what it is, then it actually makes the formula make sense and helps you to remember it. So hopefully this comes full circle for you and connects all the dots. Go ahead and give some of these a try and see how you fare.